Hello everyone, so I've received a lot of requests for a video on winds. Here it is and I hope it helps you. Before talking about winds, let's talk a bit about surface pressure. So the surface pressure of any location is plotted on a surface pressure chart. These charts have lines of equal pressure known as isobars. So this is a surface pressure chart, and the lines you see in this, these are the isobars. So isobars are the lines joining places of equal pressure. So for example, on this 1016, the pressure throughout the isobar will be 1016. In fact, it's joining all the places where the pressure is 1016. So these are known as isobars, and each isobar will have a number written on it which will represent the pressure of the isobar. So for example, this is 1024. That means that on this isobar, the pressure is 1024 hectopascals. Right. Now these isobars explain a lot about wind speeds. So the closeness between two isobars will give us an idea about the wind speed. Like if we see around this H stands for a high pressure area. So in a high pressure area, if we see the distance between two isobars, it's a lot. Over here as well. And now if you compare this distance to a low pressure area, which is over here. So in a low pressure area, the isobars are closely packed. Now the closer the isobars are placed, the higher will be the wind speed. So in a low pressure system, the wind speed will be a lot. And the distance between two isobars also tell us about the pressure gradient. Now pressure gradient means the difference in pressure. So if you see here in a low pressure area, the pressure has gone from 1000 hectopascal to 1016 hectopascal in just this distance. Whereas if you see in a high pressure area, the pressure went from 1032 to 1020 hectopascals, which is just 12 hectopascals. And here it was around 16 hectopascals. So we can say the pressure gradient is higher or steeper in a low pressure area. And the steeper the pressure gradient, the stronger will be the winds. Great, now let's talk about wind direction in the northern hemisphere. So around a high pressure area, the winds blow clockwise. And around a low pressure area, the winds blow anti-clockwise. So for example, if we look at this surface pressure chart, around a high pressure, the winds will be clockwise, like this. And around a low pressure, the winds will be anti-clockwise, like this. Also, low pressure is also known as cyclone, and a high pressure is known as an anticyclone. In the southern hemisphere, it will be complete opposite to this. So in the southern hemisphere, around a high pressure, winds will be anti-clockwise, and around a low pressure in the southern hemisphere, winds will be clockwise. Now let's talk about winds. So the horizontal motion of air is known as winds. Wind direction is always given as the direction from which the wind is blowing. And the wind direction can be either in degrees true or degrees magnetic. When you listen to the ATIS, the wind direction will be expressed as magnetic, and when you read a METAR, the winds will be in degrees true. So the rule of thumb is whenever you listen to the wind direction, it will be magnetic, and whenever you read it from somewhere, it will be in degrees true. Now wind is always expressed as a combination of the wind speed and the wind direction. For example, you're listening to the ATIS and it says that the winds are 120 degrees, 15 knots. What this means is that the wind is coming from 120 degrees and at 15 knots. So 15 knots will be the wind speed and the wind direction will be 120 degrees. So this was 0, this is 90, 180 and 270. Now how do we measure the speed and direction of this wind? So there are these instruments which we use. I am sure you have seen these. So this one is a cup anemometer and the one on the right is a wind vane. So the anemometer is used to give us the wind speed and the wind vane gives us the wind direction. Now there are two very important terms you need to know about winds, and these are veering and backing. So veering means that the wind direction is changing in the clockwise direction, and backing means that the direction of wind is changing in the anti-clockwise direction. Meaning, if the wind was coming from 360 degrees, and after some time the wind starts blowing from 030 degrees. So here you can see that the wind direction has changed in the right, which is a clockwise direction. So it means that the wind is veering. Similarly, if the wind was coming from 360 earlier and now it's coming from 330 degrees, then you can say that the wind is backing because it's coming from the left side now, and left means anti-clockwise. So these are two very important terms you need to know. Now let's talk about some important wind speeds which you need to know. I just write all the wind speeds over here, and you can maybe take a screenshot or write them down because you need to learn all these by heart. You can get a direct question on these in the exam. So these are all the important wind speeds you need to know. Now there are three things which you need to know. Now the first one is, what is a gust? So gust is a sudden increase in wind speed which only lasts for a few seconds. Increase in wind speed. The second term is a squall. So squall is also a sudden increase in wind speed, but it lasts for a few minutes. So the only difference between a gust and a squall is in the time duration. Squall can also bring in some CB clouds. Next one is a lull. So this means a sudden decrease in wind speed. You can get straight questions on these three as well, so make sure you know the meaning of three terms. Now let's talk about geostrophic winds. So this is a wind which experiences two forces, and these two forces are the pressure gradient force and the Coriolis force. So I'll write over here, first force is the pressure gradient force, PGF, and the second one is the Coriolis force. Pressure gradient force is the force which we read over here. So we talked about the pressure gradient force, and it was determined by the closeness of the isobars. So the closer the isobars, the more the pressure gradient force. And Coriolis force we did in Indian climatology, so it remains the same. I'll just add a few points to that. Now pressure gradient force is a force that acts from an area of high pressure to an area of low pressure. We can determine the strength of this force by the closeness of the isobars. And the stronger the pressure gradient force, the faster will the wind blow from high pressure to low pressure. So for example, this is a high pressure area and this is a low pressure area. So the wind will obviously blow from high to low. But the speed of this wind while blowing from high to low will be determined by the pressure gradient force. The stronger the PGF, the faster will the wind blow from high to low. So the pressure gradient force is only there because of the pressure difference. The bigger the difference, the bigger the force. So now let's recall what the Coriolis force was. So we saw in the northern hemisphere, the Coriolis force turns everything to the right side. This was the trick as well. See, and everything to the right in the northern hemisphere. And in the southern hemisphere, it was deflecting everything to the left. So this is what we'll use. And now there's a formula for Coriolis force, and this is Cf equals 2 omega rho v sine theta. Here omega is the angular rotational velocity of Earth, rho is the density, v is the wind speed, and theta is the latitude. If you remember, when we did Coriolis force, we also said one thing, that Coriolis force is 0 on the equator and it's maximum on the poles. So here if we look at this formula, it says that the latitude is directly proportional to Coriolis force, which means that higher the latitude, the higher will be the Coriolis force. And if the latitude is 0, then the Coriolis force will be 0, which is on the equator. Now another thing we can derive from this formula is that the wind speed is also directly proportional to Coriolis force. So as the wind speed increases, the Coriolis force acting will also increase. And if the wind speed decreases, the Coriolis force will decrease. Now I'll explain the geostrophic winds. So this is the northern hemisphere. There are two pressure systems. This one is a high pressure and this one is a low pressure. So we know that the pressure gradient force will be from high to low like this, and the Coriolis force will be like this because it's the northern hemisphere. The Coriolis force will be to the right. Now when the pressure gradient force and the Coriolis force will be equal, a geostrophic wind will blow, and this wind will be in a straight line and parallel to the isobars. So it will be like this. So this will be the geostrophic wind. This wind only blows when the pressure gradient force and the Coriolis force are equal, and this is parallel to the straight isobars. So if you think about it, there will be a lot of isobars around this high pressure zone, and these isobars will not be very closely packed. So maybe one isobar is like this, and there will be a point when the isobar is straight. So the wind that blows parallel to a straight isobar is the geostrophic wind. Similarly, for the low pressure, there will be isobars and there will be one isobar that is straight. So the geostrophic wind will blow parallel to the straight isobar. Now, since the Coriolis force is acting on a geostrophic wind, we can say that the geostrophic wind only occurs above the friction layer. Because below the friction layer, the Coriolis force will decrease because of a decrease in wind speed. Now I'll explain whatever I just said. So what is a friction layer? Friction layer is a layer which is supposed to be at 2-3,000 feet below which the wind is disturbed due to buildings or terrain. Like in this diagram, the friction layer is made over here, and everything below the friction layer is disturbed air. Now this air can be disturbed due to the buildings or due to the terrain. So if there are mountains or if there are houses, anything, the wind will be naturally disturbed. And since there's a lot of friction in this layer, it's known as the friction layer. So now in the friction layer, the wind speed will decrease. And as the wind speed will decrease, the Coriolis force will also decrease, because Coriolis force is directly proportional to the wind velocity. And the wind velocity decreased, so the Coriolis force will also decrease. And when the Coriolis force will decrease, it won't be able to balance with the pressure gradient force, and therefore the geostrophic wind will not exist. So geostrophic wind only exists where pressure gradient is equal to the Coriolis force, and it is not equal to the Coriolis force in the friction layer. So geostrophic wind only occurs above the friction layer. And the geostrophic wind is also not experienced between 15 degrees north and 15 degrees south of the equator, because we know Coriolis force is 0 around the equator. So I'll just write some points about the geostrophic winds that we just discussed, and please make a note of it. Now let's talk about the Bye-Balance law. So the geostrophic winds give rise to this law, and it states that in the northern hemisphere, when your back is into the wind, the low pressure will be on your left side. And this is a very obvious thing. So it is in the northern hemisphere. So now let's just talk about it in this diagram itself. So let's assume this is a person's back and the guy is facing that side. Okay, so the Bye-Balance law says that whenever your back is into the wind, the low pressure will be on your left side. So that means that the geostrophic wind will be striking this person's back. And now the low pressure is on his left side. Obviously, this is his left side and this is his right side. The low pressure is experienced on his left side. So the wind is coming on his back and the low pressure is on his left side. The person is facing this side. Perfect. Now the next wind is the gradient wind. I'll explain it here. So gradient wind is a wind which blows parallel to curved isobars, meaning it is not in a straight line like the geostrophic wind. And in a gradient wind, three forces are acting on it. And these three forces are the pressure gradient force, the Coriolis force, and the centrifugal force. We now know what are the pressure gradient force and the Coriolis force. Let's see what is centrifugal force. So when a body is rotating, there is a force that acts away from the rotating body, like this. So this is rotating, and there is a force that acts away from the rotating body, like this. That means if something is moving this way, the centrifugal force will act outside. Okay. Now since the gradient wind blows parallel to a curved isobar, like this, there will be obviously a centrifugal force acting on it, like this. Okay, now I'll tell you more about the gradient wind. So this is the northern hemisphere, and there are two pressure systems. One is a high pressure and the other one is a low pressure. We saw that the geostrophic wind will blow like this, completely straight geostrophic wind. Now let's talk about the high pressure and the low pressure separately. So in the high pressure system, the pressure gradient force will be in this direction, from high to low. And the Coriolis force will be to the right because it's in the northern hemisphere. So this is the Coriolis force, this is the pressure gradient force. Similarly, in the low pressure area, the pressure gradient force will be from high to low in this direction, and the Coriolis force will be towards the right, like this. Now let's plot the centrifugal force on both of these. Because I told you around a high pressure area, the winds blow clockwise. So when the winds will be blowing clockwise, centrifugal force will be acting outwards like this. So this is the centrifugal force. Similarly, in the low pressure area, the winds blow anti-clockwise like this, and thus the centrifugal force will be acting in this direction. So earlier, when the Coriolis force and the pressure gradient force were equal, the wind was blowing as a straight line, which was the geostrophic wind. But now, since there's an additional centrifugal force, these winds will turn and follow these curved isobars like this. So this will be the new wind. And this wind is known as the gradient wind. It is because of the centrifugal force. Now if we compare the wind speeds in high pressure and the low pressure systems, we can see that in the high pressure system, the centrifugal force is assisting the pressure gradient force. Both the centrifugal force and the pressure gradient force are in the same direction, meaning that the centrifugal force is assisting the pressure gradient force. And in the low pressure area, the centrifugal force is opposing the pressure gradient force. So we can say that if we assume all isobars are equally spaced, the gradient wind speed around a high pressure area will be greater than that of the low pressure area. But this is just a hypothetical scenario. We know that the winds are always stronger in a low pressure area, right? So we can also say that the gradient wind in an anticyclone is stronger than the geostrophic wind, because in the geostrophic wind there was a pressure gradient force and the Coriolis force. And now since we are assisting the pressure gradient force in the anticyclone, the wind speed will be more around the anticyclone and it will be a gradient wind and not the geostrophic wind. Alright, so gradient wind is done. Now let's talk about winds below the friction layer. So we know that the wind velocity is less in the friction layer due to the disturbances in air because of terrain and everything. We saw it in this diagram that even the Coriolis force decreases. And obviously the Coriolis force will decrease because the wind velocity will decrease, and the wind velocity decreases because of all the friction in this layer. So the wind that blows in the friction layer is the surface wind. And we'll talk about the surface winds now. So this is again in the northern hemisphere. There's a low pressure area, there's a high pressure area. And this was the direction of a pressure gradient force, and this was the Coriolis force to the right. And we had the geostrophic wind like this, if both were equal, right? But in the friction layer, we know that the Coriolis force has been reduced. So when we reduce the Coriolis force, let's say this is the new Coriolis force, which is less. Now since the Coriolis force is lesser, it won't be able to balance the pressure gradient force. As a result, the pressure gradient force will pull the geostrophic wind towards itself like this. You just think about the pressure gradient force and the Coriolis force as two strings which are pulling the geostrophic force equally from both sides. Now when the Coriolis force is reduced, obviously the force from one side of the string is reduced, so the pressure gradient force side will pull the geostrophic wind towards itself like this. And this is the surface wind. And we can say that the surface winds will blow across the isobars, because now this won't be parallel to any isobar. It will be cutting through the isobars like this. It will be just cutting through the isobars. So we'll say that the surface winds blow across the isobars. Perfect. Now what will be the angle and the speed by which the winds will change? Because we saw that there was an angle by which the wind changed, and since the wind velocity decreases in the friction layer, we need to know that by how much value will the wind velocity decrease. So the wind is backed by 30 degrees and the wind speed is decreased by 50%. This is the scenario on land. Now on sea, since the friction layer is more stronger on the land, when we talk about the sea, the backing angle will be just 10 degrees. So now let's see a question on this. So in this question it says that the surface winds are 360 degrees at 20 knots. What will be the wind at 3000 feet? First we have to understand what he's asking in the question. So in the question we are given surface wind and he's asking us the wind velocity above the friction layer. Because the surface winds come in the friction layer, and we saw that in the friction layer the wind speed decreases and the wind backs. So he's just asking the opposite of it. So he's given us the surface wind and is asking about what will be the scenario of winds above the friction layer, which we can say at 3000 feet. So now we know that the wind speed at 3000 feet will be more than what it is at the surface, because on the surface the friction layer reduces the speed. And we also know that the wind is backing on the surface, so at 3000 feet it should be coming from the right. Now we'll use the 30 degrees and 50% rule. So on the surface the wind is coming from 360 at 20 knots, which is in the friction layer. So obviously above the friction layer this wind should be coming from this side. And if we go right 30 degrees from 360, it will be 030 degrees. So the wind is coming from 030 degrees and the wind speed on the surface is 20 knots. We know that the wind speed is 50% on the surface to what it is above the friction layer. So since it's 20 knots on the surface, it will be 40 knots above the friction layer. So the wind at 3000 feet will be 030 degrees at 40 knots. I hope you understood this question. In this, we just reversed whatever we learned about the surface wind. We learned that whatever the wind was coming above the friction layer, the surface wind comes from the left of it. And now if we are given the surface wind and we have to find the wind above the friction layer, so obviously the wind above the friction layer come from right of what the surface wind was coming from. Okay, so surface wind is done. Now let's talk about some other winds. Okay, so the next one is the sea breeze. This one is the sea breeze and this is the land breeze. We'll talk about both. So now what happens in the coastal areas is that during the day, the land heats up more quickly than water. So let's assume this is the land and this is the water. Okay. So because of the sun, the land heats up faster than water. This is a property of land. So there is a low pressure experienced on the land. This low pressure is because the air starts to rise because land is heating up and the sea is not heating up that fast. So there is a low pressure experienced on the land and a high pressure is set above it because all the air molecules that are rising from the land are coming up. So which will lead to a high pressure above and a low pressure below on the ground. Now on the sea, since it's heating lesser than the land, a comparatively higher pressure is experienced near the surface. So here will be a high pressure. Now this is not a very high pressure. This pressure is just higher than this. Because land was heating faster, so there will be a comparatively higher pressure on the sea. And at an altitude above the sea, there will be a comparatively lower pressure to what it was here, right? So this is a pressure system set in the coastal areas during day. The land heats up, which creates a low pressure on the surface and high pressure above. And on the sea, there's a comparatively higher pressure on the surface and a low pressure above. So now the wind will start blowing from high to low pressure, like this. On the surface, and there will be a cycle formed because this blows from high to low and then over the surface the air molecules were rising, so this will go up and again there is a pressure difference above here, so the wind will go back to low pressure from high and it becomes heavy and starts sinking. So this is a cycle and this wind blows from the sea to the land and is known as the sea breeze. Now a similar thing happens at night. It is known as the land breeze. Now this is after the sunset when the land cools down and the land cools down faster than the sea. So a reversal of sea breeze takes place. So it is high pressure over here because all the cold air sinks. And since it's a high pressure over here, there will be a low pressure above. There's a comparatively lower pressure on the surface at the sea compared to this high pressure. And there's a higher pressure over here as compared to what it was here. So again, another type of cycle sets in which the winds blow from high to low pressure like this. And here the air was sinking because of the temperature and a cycle is set like this. Now out of these two, sea breeze is stronger because the sun is there. And because of the sun, there is a bigger pressure difference between these two. And the bigger the pressure difference, the more the pressure gradient force will be and stronger will be the wind blowing from sea to the land. So sea breeze is stronger. Now the next two winds are experienced in the mountains and valleys. So this one is the Katabatic wind and this is the Anabatic wind. Katabatic wind is the one which flows down a valley at night. So what happens is that at night the air around the valley becomes cold. So all this air around the valley becomes cold and cold air sinks. Same happens on this side as well. Now these winds which blow down the hill at night are known as Katabatic winds. So I'll write at night down the hill. Now what happens during the day is that all the wind that's in the valley starts rising because of the sun. We know hot air rises up. So the wind that goes up the hill is known as the Anabatic winds. I'll write during the day and up the hill. So these two were the winds that blow in a valley. Now which one do you think will be stronger? The Katabatic wind is stronger. The reason is that in the Anabatic wind, the wind is blowing opposite to the force of gravity. So this is gravity by the earth. And this wind is going up, which is opposing the force of gravity. And if you see over here, the Katabatic wind is also coming down and the force of gravity is also pulling it down. So this is stronger. And it is stronger because it is not opposing the force of gravity. Okay, now the last wind is known as the Foehn wind. So this is a warm, dry air that's blowing on the leeward side of the mountain. So this wind over here is the Foehn wind. This part. I'll explain how it's formed. So when it rains in the mountains, there's a lot of moisture around and the air is moist. Now when this moist air is forced to climb up a mountain, maybe due to some wind. So for example, there's a wind from this side which is forcing the moist air to climb up the hill. So this moist air will quickly become saturated and will cool down, and clouds are formed because when it reaches the condensation level, we see the formation of clouds. So the winds were blowing and this moist air started to climb and clouds are formed. Now these clouds will give rainfall, making the wind lose its moisture. So now the wind does not have moisture over here. It will not be a moist air but a dry air. And if the dry air is stable, it will come down on the leeward side of the mountain like this. We know that the stable air comes down, and when the air will be coming down, its temperature will increase. Because when you go up, the temperature decreases, and when you come down, it increases. So now this is dry and warm air on the leeward side of the mountain. And this dry and warm air is known as the Foehn wind. And this wind is very turbulent because of the friction it encounters when coming down. And this friction gives a lot of turbulence. Okay, so with this we come to an end of this video. I've covered all the important stuff from this chapter from the exam point of view, but I would suggest you go through the book real quick before sitting for the exam. Let me know if you have any questions, and thanks for watching.